Today's topic is a sparsely labeled dataset for action classification and localization. It is also called SLAC, and my name is Kamran Ali. So, since this dataset is about action recognition and action localization, so what is action recognition? Action recognition is basically a task to recognize the actions within a clip and assign automatic labels to these clips. Another task that is associated to video analysis is action detection. In action detection, we have a clip, and within each frame in a clip, an action is happening, and we have to find not only the label of the action, but also the bounding box across the object performing the action. So those videos were trimmed videos, and in trimmed videos, we have action in each and every frame of a video, and we have to find the actions within those frames. Similarly, we have untrimmed videos as well in video analysis, where we have a long video, and within this long video, we have actions within certain frames, and certain frames belongs to background as well. So temporal action localization is usually a task that is performed on untrimmed videos. And in this task, we actually find the frames associated to a particular action. In this case, we are concerned with soccer penalty. So we have to find the start and end of a frame within this sequence. There is another task that is performed. It is called spatio-temporal localization, and spatio-temporal localization, we not only find the spatial location of the frames, but also the bounding boxes and the temporal location of the frames. So the motivation behind this dataset and this paper is that with the advances of deep learning, the deep networks are mostly dependent on large data sets. So the larger the data sets, the better the performance. So in image domain, we had Caltech 101, the dataset that we had before deep learning, and Caltech 101 contains 101 action classes. Then we have ImageNet, which contains 1000 action classes, and we have Coco dataset, which is also used in image domain. While in video domain, we have UCF 101, which was introduced before deep learning era, and it is still used frequently in video analysis. We have HMDB 51, which is also used in video domain. We have Kinetics, we have Sports 1 million, we have ActivityNet, AVA. So the datasets for video action recognition and localization are divided into two parts. First is action classification, and for that we have UCF 101, which contains 101 actions and 13K annotations. And since this dataset is for action recognition, it does not contain the localization for temporal localization for temporal recognition. We have HMDB 51 as well, which contains 51 action classes, and 7K annotations. We have Kinetics, which is consists of 400 action classes, and it contains almost 300K annotations.
So it's the largest
dataset. Sports 1 million is largest.
Yeah, but action datasets are largest.
Yeah. So Sports 1 million has 1.1 million annotations, but since this is sports dataset, so it cannot be used for daily activities. For temporal action localization, we have datasets like Thomas 15, which contains 101 actions, and it contains 21K annotations. And since it contains temporal localizations as well, so it can be used.
On UCF 101. Our dataset also.
Yeah.
Yeah,
right. We have ActivityNet with 200 actions, and there are 23K annotations in ActivityNet. We have Chariots for 157 actions, and 67K annotations, AVA with 80 actions and 197K annotations. So these annotations, as you can see, are very very small for deep learning networks. So to train deep learning networks, we need larger amount of annotations. So the SLAC is basically introduced to overcome this problem. So in SLAC, we have 200 actions and 1.75 million annotations, and it contains the localization as well as the recognition tables as well. So the common threads of the previous datasets are that they are manually compiled in a way that a human technician sits down and he or she labels the videos according to the action that is performed, and he or she has to decide the start and end of a frame within the temporal domain. So it is very time consuming and very laborious task, and it is prone to error. So and the action boundaries are usually very blurry due to action movement, due to human movement. But in SLAC, they have come up with an automatic sampling of clips based on some classifiers, which we'll discuss. And the data collection pipeline of SLAC is in such a way that initially we take videos from the internet and deduplicate those videos, because some of those videos are same but they have different durations in time, or some similarities based on contrast and saturation. So we have to deduplicate that, and then we detect shots from each video, and those video shots are used for person detection because we are concerned with human action recognition. So we don't want those videos which does not contain persons. Then we come up with a sampling distribution for the sampling of clips from this huge video data that is acquired from the web. So for this sampling distribution, we actually train 2 image classifiers, and based on the output of these 2 image classifiers, we come up with a sampling distribution. We will discuss these steps in detail in the coming slides. So let's first look at have a glance on SLAC dataset. It contains 200 actions and 1.75 million annotations, as we discussed. The average length of the videos is 2.6 minutes. And the workforce that is used to acquire this 1.5 million annotations contains 70 annotators who work 6 hours a day, and the total time that consumed during this annotation period is 10.5 days. The training, validation, and testing split is as follows: 5,000K videos are used in training set split, 6,000 validation videos, 12,000 testing videos. The challenges that they faced and they overcome during this the compilation of this data set is that we have large imbalance in the negative and positive samples. The negative samples are larger in number as compared to the positive samples. And not all of those negative samples were informative and useful for the training of networks. So they dealt with these 2 problems. So let's look at some negative samples. Let's suppose we are interested in the action of archery, and this is the positive sample. The negative sample that can be of a sample which does not contain a person. Another negative sample is of a sample containing a person but does not contain a context. The third and the hardest negative sample is of no action, where there is a person and there is some context, but there is no action. So the main goal of this paper is also to come up with a sampling distribution that is biased towards this harder negative samples, to get these negative samples, which are more informative. So 1.1 million videos for 200 classes were initially acquired from the internet, usually from mostly from all of them from YouTube. Then we do internet deduplication to remove the redundant videos. Then we do external deduplication across different data sets to remove the redundant videos. The internet deduplication steps are as follows, as we have many 200 classes, action classes, and for each action classes we will be having many videos initially. Let's take one action class, swimming. Then we will be having, let's suppose here we have 5 videos associated to the action class swimming. We compute the features of these 2 videos and do the thresholding on the features of these 2 videos. Similarly, we do this for each peer, compute the thresholding and do this thing. And then we come up with some connected components based on this procedure.
So it's basically clustering. Clustering.
Clustering involves, yeah, you can say one cluster. So from this connected component, we take one video, which will be the representative of this set. And in this way, we remove the redundant internal videos from SLAC. So using this procedure, they removed 171K videos from SLAC, within SLAC. And they did the external deduplication across different data sets as well, in such a way that the videos that are present in SLAC are being found in the different data sets, like in kinetics, and the same procedure is applied manually. And then they removed 4,000 videos from kinetics, almost 2,000 videos from activity videos from SLAC that is also present in ActivityNet, videos that is present in UCF, and videos.
So how did they do that? When they're saying that manually, what is it?
They actually, like if the action is swimming, then they took the list of the actions that is similar to swimming, like backstroke and things like that in the other data sets, and they compute the cosine similarity of the features, and then did this thing.
But that's not manual, it's automatic.
I mean, the listing was manual.
Oh, I see.
So since we are concerned with human action detection, so initially we have to remove the first negative, which is with no humans. So for that, we train a person detector, but as a pre-processing step, we do short detection on the videos, and then we train the person classifiers. So the flowchart or the flow diagram of the person detection is that we have original video, we detect the video shots, then from each video shot we sample 2 frames randomly and feed these frames to a person detector, which is a faster RCN. So those videos in which none of the frames contains a person score higher than a threshold are removed from the dataset. In this way, they removed like a couple of thousands of videos within this SLAC. So initially we were concerned with 3 negatives: no person, no context, no action. And now after doing the person detection and removing the no person videos, we are left with 2 negative samples within the video. So the purpose of this paper is to, as I mentioned, is to come up with a sampling distribution that is biased towards the no action negative samples, which is more informative. So to achieve this goal, they trained 2 classifiers. One is YouTube video-based, frame-based classifier, and the other is Google image-based classifier. So let's look at them one by one. The YouTube frame-based model is trained on 500 YouTube videos for each action class that is acquired, apart from the 1.1 million videos that are initially acquired for SLAC.
So how do they make sure they make sure that these 500 videos are not in that SLAC dataset?
I'm not sure. Yeah, they haven't mentioned it, but they have mentioned it that this is different from that set.
Yeah.
So then to remove the videos without persons, they did the same procedure. They detected the video shots and then fed the frames from the video shots to person detector, and then those samples, those frames with high person score are fed as a positive sample in the classifier, and those frames with low person score are fed as a negative sample to this classifier. And the Google image based classifier is trained on 300K images obtained for each action class from the from Google. And then the images are fed to the person detector to remove the images without person, and then the action classifier is trained on these uh, images.
So these both action classifiers are image based, not the video
Yeah.
based, like this single image.
So based on the output of these two videos, they do a query by committee procedure, which is a consensus between these two classifiers. And doing this query by committee, they come up with a sampling distribution for the sampling frames. So let's see how they do this. We have the original video. We do the video shot detection. We select one frame randomly from each shot. And in this way, we have a set of these randomly selected frames from the video shots that is called X, capital X. So each frame from this capital X is fed to both of these two classifiers, YouTube frame classifier Y and Google image classifier J. And based on the output probabilities of these two classifiers, we get a probability Rx for this particular frame X. So there are three components in this probability Rx. One is, as it is shown in this box, the probability of frame X containing the label C, and this probability comes from the classifier Y, video YouTube frame Y. The probability PGC is the probability of frame X containing the action C from the Google image based classifier. So in this term basically ensures that we are not considering the no context negative samples within the sampling process. The second term is the KL divergence between the class-wise probabilities of this particular action, this particular frame X. The third term is the similarity of frame X with all other frames in the capital X, and this term ensures the similarity of the sampled frames. Ensures that the sampled frame is the representative of the video. So based on this probability Rx is calculated for each and every frame in X. So at the end, we will be having a probability distribution for each frame. And based on this probability distribution, we sample those frames which has high probability during the clip formation. The 2-second clips are formed in such a way that the sampled frame that is sampled based on this probability is extended into 2-second clip in such a way that 1 second is added on both sides of the frame.
These are the positive examples.
These contain positive and negative, both of them.
But then what's the, okay, let's see what you, next one.
Yeah, so doing this sampling and converting the frames into a 2-second clip, we acquire 1.75 million clips. And now these clips have to be annotated manually. And
So
this,
can you go back?
Yeah.
Yeah, so you get this, like you had a figure, right, for the distribution. So you apply, you're saying threshold or something. So you get this Rx,
Yeah.
right? So this Rx is for each of the frame
each of the frame in X.
in X. Then you get take this and find a distribution.
Yeah.
many frames have this num RX, how many frames this distribution, right?
Yeah, I mean, within, let's suppose in X we have 3 frames,
Yeah.
so we will be having 3 probabilities.
Three probs,
So this is the
okay.
probability distribution, discrete probability distribution.
Yeah, but I mean, then there may be some more frames.
Yeah, exactly.
Exactly same value, right?
Yeah, exactly.
That, so you can have, 3 frames may have value 0.1.
Yeah.
So then distribution means that 0.1 has 3 numbers, and then other may have 0.5, there are 6 outputs.
Yeah.
That's a distribution. If you just put the confidence, it's not distribution. Distribution means counting.
Yeah.
How many of these have the same probability?
Yeah, they do this for each video, so.
Mm-hmm. So given that distribution, then what's the purpose that you want to do what? You want to identify, so you apply a threshold on that, right? Or what do you do?
No, this is not threshold. They do the normalization of this. This is
Okay.
non-normalized probability.
Yeah.
So they do the normalization of that, and then after normalization, they pick those frames whose probability is high. And for the positive frames, like to make sure that the frames contain actions, they do threshold on this thing, on this first term.
So the frames which have high probability tells you that this has an action?
Yeah.
Okay.
Yeah.
So you select those, so they're telling you that these frames have action.
Actions. Yeah.
So around that you pick the two second.
Exactly.
Right? Because earlier you were saying it was negative. These are basically positive.
No, actually, this term, Kale divergence term, is introduced to bias this towards the negative samples, which are no action negative samples, which are more informative. Otherwise, we would be just fine with this thing, with this first term.
So it gives you, this helps you to select the frames which has some action.
Which has some action or no action.
No action.
Yeah.
Then what is the selection for? Because if you are getting both, then you don't have to select. Anything will have either action or not action.
Yeah, but this will be fetched to the annotation tool, and the final annotation will be done by the.
Yeah, I think this is pretty confusing. We have to spend a lot of time. But
Yeah,
I'm convinced.
There are 3 kinds of negatives in there. So they want to get the hard negative and clips with actions.
Mm-hmm.
So this gives you a probability, high probability for those which has actions and which has hard negatives which have no action, but there is person and context. So this then is used to crop the clips, and the clips are passed to the human annotators to annotate them.
Okay, so that continue, then we can discuss this. Yeah.
So the annotation guideline that is provided to the human annotators are in the form of definitions, clips, images. So let's take an action of clean and jerk. The definition that is provided to the human annotator is as follows: for the clean and jerk, a 2-movement weightlifting exercise in which a weight is raised above the head following an initial lift to the shoulder level. And the images and clips are also provided to reduce the ambiguity, as it can be seen that this is a positive action for clean and jerk, and this is the negative because he is in preparation stage. And this is the annotation tool that is being used by the annotators to annotate these sampled clips. And this is a particular action for biking, and this green box that is assigned to these clips indicate that these are positive samples, and the red one indicates that these are the negative samples. For action annotation quality control, they assigned same labels, same actions to the same annotators. And they also used a golden set which contains 10K clips, labeled clips. And using this 10K labeled clips, they measure the accuracy of each annotator, which is the average accuracy is 94%. So now let's talk about some results on SLAC. First, we will talk about action recognition benchmark. For action recognition benchmark, they use the network RES 3D containing 34 parametric layers. Initially, they trained this ResNet on the training set of the SLAC and then did the validated on the validation set. They used two measures for this. One is class agnostic clip 1 accuracy, which is the number of clips that are predicted correctly divided by the total number of clips in the validation set. The other measure is class aware clip at the top 1 accuracy, which is the frame. These clips are grouped based on their labels, and then within each label they report the top 1 accuracy and then average out throughout the classes.
Class.
Yeah. They use three inputs for that. One is RGB, and for RGB they got these accuracies, 54.3 and 76.5. They used optical flow as an input, and for optical flow they got a bit of a less inaccuracy. And when they combined RGB and optical flow, they got better results. Then they tested this trained ResNet on the test set of SLAC using the same two measures, and these are the accuracies that they got. They also used it, evaluated it on transfer learning task, where they pre-trained the model on SLAC and then fine-tuned it on target dataset, first as UCF 101. And when it is used, when it is fine-tuned without pre-training, then the accuracy is mentioned here, and when it is pre-trained with SLAC, then the accuracy is quite high, and which is quite obvious. When they used optical flow as an input, then the accuracies are mentioned as below. They fine-tuned this pre-trained ResNet on HMDB as well, and these are the accuracies that they reported. They fine-tuned using kinetics as well, so these are the accuracies. Then they compared with other pre-training datasets, like they compared with kinetics. When they pre-trained their ResNet model on kinetics, they got these accuracies when fine-tuned on UCF. And they also compared with Sports 1 million as a pre-training. And as it can be seen that when they pre-trained their model on SLAC and fine-tuned on UCF, they got better results. They did the same for HMDB 51 and also got better results. And when they used kinetics, in case of kinetics, they also outperformed other pre-training datasets. So they also compared their ResNet model pre-trained on SLAC with other models like long-term temporal convolutions, TSN, two-stream 13D, and these are the reports of these state-of-the-art models. And these are the two results of the ResNet pre-trained on SLAC. So as it can be seen that only two-stream 13D kinetics pre-training outperformed the two-stream ResNet model that is used in this paper. And it is due to the fact that this two-stream 13D is using a very sophisticated method to obtain the optical flow. But here they are using a very simple method to obtain the optical flow. Now let's see the evaluation of SLAC on temporal action localization. And in this case, they evaluated it on Thomas 14 and ActivityNet. The network architecture they used is CDC network. And let's see what this CDC network is. Initially, we have a proposal segment with dimensions as 3 channels. The temporal length is L and the spatial location is 112 by
So
112.
do they tell you like how do they get these proposal segments?
Yeah, actually, when they used it for 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 Thomas, they used another proposal network,
Hmm.
and for ActivityNet, when they evaluated it on ActivityNet, so they used another proposal.
But just tell me in any proposal network, what exactly do they do?
The name of proposal networks?
No, I mean, how does it work? Like, so you have a long video,
Yeah,
right?
yeah. We have a long video, and we feed this to that network, and that network gives a coarse temporal localization of that, and that 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 is considered as a initial proposal for that.
So it gives you like a different segments.
Yeah, it is different segments. Then they have a classification layer for that, a softmax layer, which will select one of these segments based on the features that are
So
extracted.
that's what they do, but here the input is the segment, right?
Here the input is the
segment of the
proposal network.
So proposal
Is another network.
another network.
Yeah.
And how does it work? Like how do they get proposal?
Yeah, they initially feed the video to the network, and they extract some features, see 3D features on that, and then they have the anchor segments for that. Different network
Very
has
similar to the like RCN and proposal network.
somewhat similar. Yeah,
Template.
exactly. So this proposal segment is fed into this 3D convnet, which is the first 5 layers of C3D. And since due to the max pooling and convolutions, we get a reduced dimension along the temporal domain. So we are doing the frame-wise localization of this segment. So we have to upsample it in the temporal domain and downsample it into the spatial domain. So for that, they are using CDC filters. As it can be seen that the the length of the temporal domain is increased and the spatial dimensions are decreased. And they keep on applying this filter until we get the original length of the uh, temporal domain. So then we feed this 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 thing into the softmax layer, which will give us the probability of these frames containing the action. Here k plus 1 represents the action, k is 200 and 1 is for the background. Now they trained their network on this CDC network on SLAC, and then they evaluated it on the testing set of Thomas dataset, and for that they used the measure of MPA with the intersection of union. These are the thresholds that are used for intersection of union, and without pre-training they got these measures, these accuracies. And with pre-training on sports, when they pre-trained on sports 1 million, they got these precision values. When they pre-trained it on SLAC, they got better results as compared to the sports 1 million. And then they also compared their CDC network with RC3D network that is pre-trained on sports 1 million, and as it can be seen that the performance of their network is better as compared to that. But when they compared their results with SSN, the SSN outperformed their accuracies, their precision.
So what is this?
Yeah, it's a structured segment network. So I went through this paper.
The recent paper?
Yeah, it's 2016, I guess. Something.
Oh, is that the one from the Cats Noik that I told you the lady?
No.
The different.
No. So they also evaluated their trained CCD network on the validation set of ActivityNet, and they used the same measure. Without pre-training, they got these precision values, and when they compared it with pre-trained on sports 1 million, they got these Mayers. When they compared with pre-trained on SLAC, they got better results. And again, when they compared it with RS3D and SSN outperformed it. Oh, yeah, then that was, yeah. So this is the result for the activity net. So when they used it before, actually they do some refinement as well. So when the temporal localization segment is obtained, they do some refinement in such a way that they adjust the temporal location of the frames accordingly. So before refinement, they got these Mayers, and after refinement, they got these Mayers. And when they evaluated it on pre-trained sports 1 million, they got this Mayers, and after comparing it with pre-trained on SLAC, they got better results in some of the higher threshold values. So that's it.